Good day and welcome back to part 2 of our discussion on areas. In the previous video, we reminded ourselves of some of the basic properties and important formulas related to sigma notation. And in this video, we are going to transition into this new question or topic of finding an area enclosed between curves. And at this point, it's, I think, very unclear in terms of where we are going with this idea and topic and how it relates to all of our previous calculus-based discussions. But within a few sections, that will be made clear. But for now, let me just remind you of our initial starting point for this course. We began by discussing these two seemingly unrelated questions of finding slopes of tangent lines or instantaneous velocities, and then from the ideas we were able to build up to this thing we call the derivative, and then the course just took off from there. If you can stick with this idea of finding enclosed areas, it will eventually connect back to differentiation, and in fact it leads very nicely into our last major topic of the course, which is something called integration. But for now, let's get to the question of enclosed areas. So the common question we are going to have for the remainder of this section is, can we find the area of the region that lies under a curve from x equals a to x equals b? And throughout our conversation in this section, we are going to be assuming that the function we are dealing with is positive on this interval of interest. And what we are trying to determine is a number that represents that enclosed area. So it's enclosed below by the x-axis and above by that curve given by the function y equals f of x. Now, if we happen to have an area that was circular, triangular, a rectangle, maybe even a trapezoid, we would have familiar geometric formulas that we could use to quickly evaluate and determine that exact area. But as we can imagine, most curves we encounter are not going to be these familiar geometric shapes. So instead of trying to evaluate or determine the enclosed area in one single step, what we are going to have to do is first approximate that enclosed area, and then think about how we can improve upon our approximation, and maybe in fact, how can we make that exact? And thinking along these lines, what is the easiest geometric shape for you to calculate the area of? And I find most students would typically tell me a rectangle. You think immediately the area would be what? Length times height. So what we could imagine doing, at least from a procedural perspective, is taking this enclosed area that we're hoping to find and somehow approximating it with rectangles. And in fact, what we could do is maybe think of taking this interval from A to B and somehow breaking it up into a bunch of different subintervals, and we could let each one represent the base of some rectangle. And if we imagine drawing in all of these rectangles, we could calculate the area of each one individually, add them up, and we would get an approximation of the area enclosed under the curve. And note, we know it is only an approximation because we can see all kinds of error that's taking place here, but we could maybe imagine how we could make this a better approximation. And I'll let that kind of percolate in the background. For now, though, let's investigate a very specific, concrete example. For the curve y equals x squared, with x varying from 0 to 1, let's use 4 rectangles to estimate that enclosed area. So graphically, we're thinking the enclosed area is from 0 to 1, and we can very clearly see it in this picture. And what I would like to do is approximate that area using 4 rectangles. And because these instructions are rather vague, that does leave us quite a bit of freedom to work with. And maybe just for convenience, what I would think about doing is taking this interval from 0 to 1 and breaking it up into 4 equally spaced subintervals. So we can go from 0 to 1/4, from 1/4 to 1/2, 1/2 to 3/4, and 3/4 to 1. And note how we could get the length of each one of those subintervals. We can say that the length of the entire interval is 1, and we want to break it into 4 equally spaced subintervals. And in our future discussions, we will refer to that quantity as being delta x. And once we've determined these subintervals, which are playing the role of the base of a rectangle, there is another big decision that we have to make. How will we determine the height of each rectangle? You simply need to pick one point in the interval to determine the height. And you could pick that point in the interval to maybe be, say, the left-hand endpoint of the first interval, the right-hand endpoint, or anything in between. But for convenience, I prefer to always work with kind of the same pattern. So let's do this first using the left-hand endpoint. So the first rectangle doesn't even appear to be a rectangle because there's no height associated with that. The graph of x squared goes through the point 0, 0. Then at 1/4, if we go up to the curve and let that determine our height. At 1/2, we go up to the curve and let that determine the height of the third rectangle. And then similarly at 3/4. And so we now see in our picture, I'll say 4 rectangles drawn. And if we add up the areas of each one, which we most definitely can do, we get an approximation of the area enclosed under the curve. So we're not trying to claim this is the exact area. We'll come to that in a bit. For now, we are simply approximating the area. So that first rectangle has base length 1/4, and the height is determined by substituting the left-hand endpoint of the interval 0 into the function x squared. Plus, the next rectangle has base length 1/4, and its height is determined by plugging 1/4 into that function. And note we can see this point on our graph very clearly. That would be the point 1/4, the input, 1/4 squared, the output. Then we add on to this the area of the third rectangle, base length 1/4, and the height is determined by substituting 1/2 into the function. And then we add on the area of the fourth rectangle, base times height. And if you do the arithmetic, these 4 numbers add up to be the quantity 7/32. And this is an approximation to the area enclosed under the curve. Probably not the best approximation, as we can see there's quite a bit of error involved. Is it an overestimate or an underestimate? It is most definitely an underestimate, because our rectangles are purely contained underneath the curve and we've missed area enclosed underneath the curve. And this is something which is known as a left-hand approximation. So the L4 would indicate that this is a left-hand approximation with 4 approximating rectangles. And in general, we would say L sub n would be the left-hand approximation to the area enclosed under the curve with n approximating rectangles. And as you are probably guessing at this point, there's nothing special about using the left-hand endpoint of the interval to determine the height. What I would like you to do is to pause the video, give yourself a minute or two, and see if you can do a similar computation and approximate the enclosed area using 4 rectangles where the height is determined by the right-hand endpoint of each interval. And once again, we need to break our interval up into 4 subintervals. And for convenience, I'm going to make them all equally spaced. And what I would like to do is draw in now 4 rectangles. I'm going to use the base, once again, as each of these respective subintervals. And I'm going to determine the height of the rectangle by going up to the curve at the right-hand endpoint of the interval. So in the third interval, we're using 3/4, and on the fourth interval, we're using the right-hand endpoint of 1. And adding up the areas of these 4 rectangles, we get a different approximation for the area enclosed under this curve. So just one at a time, working from left to right, we have the area of the first rectangle, plus the area of the second rectangle, plus the area of the third rectangle, and finally the area of the fourth rectangle. And these numbers add up to 15/32. Once again, this is just an approximation, and from our picture, hopefully we can all agree that this is a very obvious overestimate. And this number and this computation is something we will refer to as being R sub 4. That would be the right-hand approximation with 4 approximating rectangles. And once again, the idea is we're going to approximate the area underneath the curve using 4 rectangles that all have a base of equal length, like we've done, and the height is determined by the right-hand endpoint of the interval, hence the R. Once again, in general, we would refer to Rn as being the right-hand approximation to the area underneath the curve within approximating rectangles. And the height of the rectangle is determined by using the right-hand endpoint of that interval. And at this point, we have what? 2 approximations to the area enclosed underneath the curve. And you're wondering, one is an underestimate, one is an overestimate. How do we come up with a better estimate? And in this case, if you're thinking take the average of the 2, yeah, that's certainly true. That would give you a better approximation. But in general, how can we come up with the best possible approximation? And in general, we come up with a better approximation by using more rectangles. The more rectangles we use, the better approximation we should find. So with that in mind, how could we get the exact area? And if you're thinking use infinitely many rectangles, I agree with that idea theoretically. What we need to do is take the limit of the number of rectangles as n goes to infinity, with n being the number of rectangles. So if we could maybe figure out kind of what R sub n would be, the exact area should be the limit as n goes to infinity of R sub n. And in fact, we will start off our next video by investigating our previous example and seeing if we can determine that exact area underneath the curve. So stay tuned and take care.